So as far as what you're looking to pick up next, are you looking to continue with the counting method stuff, or do you feel like you've more or less got it to a point where you can start working on that more or less yourself?
Yeah, I think it should be okay. Is it like really prevalent in like 3, 4 or
It's non-existent in 3 and 4,
oh,
basically.
okay.
It'll make an appearance only in the Bernoulli sequence, simply because it's the coefficient of the Bernoulli sequence, the selections equation specifically.
Okay.
But as far as like the methodologies of solving those particular questions, it's exclusively 1 and 2.
Yeah, that's fine. Because I more so just wanted to be like good at it. So like when I do exams, I'm like I don't need to
Mm.
skip the probability part.
Oh, sure. Yeah, okay. Well, then, no. That's. Um, I mean, they might show up in other exams that are non VCAR, but that's only because they're trying to do different things, I suppose. It just doesn't show up. But cool. Okay, so that would mean continuing on with discrete then. Let me pull that up. Are we? Probability discrete. I believe we got through the first doc on discrete up until, yeah, we talked about up until here, conditional probabilities.
Yeah.
Um, this wasn't necessarily the priority for you, that was the counting method stuff. Is this something you want to practice, or do you want to continue on?
Like as in probability tables.
Just all the stuff that includes with probability tables. So whether it's conditional probability stuff, whether it's solving the unknowns in a table, all of these like key
Nah,
examples.
I think it's pretty straightforward.
That's straightforward. Awesome. On to statistics. Okay, so key statistics we're looking at are going to be the mean, variance, and standard deviation. That's going to be applicable to basically all of the probability types that we do. Although you'll find that they all have their own little nuances as to specifically what you're going to actually do to calculate them. So the fancy equation of the mean is using this sum symbol. Basically, what this is telling you to do is multiply all of the x's with all their associated probabilities, and this, just like as a fun little FYI, is basically saying starting at I equals 0, so index 0 of the table, all the way up to I equals n, where n will be the end of the table. That's how you read that syntax there. What that means for you is you're literally just taking this table and going that one multiplied by that one multiplied by that one, and then just repeatedly adding them all together. Nothing difficult, only insofar as the ability to actually calculate all those numbers back to back without making a mistake in a calculator or otherwise. What does it actually tell you? Well, it tells you the weighted average of the data set, whatever you're looking at in particular. So in this case, we get a number 1.2, which should make a decent amount of sense considering that zero point 0.4 is the biggest probability, and then it's slightly leaning right because you've got 0.28 and a little bit over. So it should be slightly right of x equals 1, which is what we get. It's where more or less most of the probability is centered. Sometimes you don't just do regular e of x, sometimes you do e of a function of x. This is more a textbook thing than an exam thing, although technically speaking, this, which is used in the calculation of variance, is required because it's a calculation for variance. This sort of stuff is unlikely to appear on its own. In textbook it does, so we'll have a look at it. Basically, this is a multiplier, or sorry, this is a transformation on the x before multiplying it by the probability. So effectively, instead of doing 0 times 0.2, you're doing 2 times 0 plus 3 and then times 0.2. And it's just a transformation on the x's.
All right.
In the case of linear, you can actually do this kind of replacement substitution. So instead of doing exactly what I just said there, you can take the coefficient a at the front. There's a fancy reason why, and the plus b is just sort of chilling out the back. This doesn't look like you can do it, but there is a reason why. I just haven't looked into it
And
too
the B
much.
doesn't get divided?
Yeah, it's not as simple as just like like this isn't like a bracket as in like e times this. Um, there's, I mean, maybe the. Let's have a look. Let's see if Unit 1 and 2 actually talks about it, why it exists. No, it's not going to be in there. It's going to be Unit 3, 4 because it's statistics. Let's see if they have a little proof for it, just for fun. Just chilling there. Keep scrolling a little bit. Oh, hang on. They had one for variance that took this and then did some funky stuff with it. They didn't actually prove this one. Oh well. There's some fancy shit. Actually, no. There's it's in binomial, but it's probably fine. Not really. I'm sure if you back.
Yeah, I'm back.
Yeah, I mean, you didn't really miss anything. I was just trying to look for some proofs there.
Yeah, I don't
Um,
know what's keep on happening every like lesson, but
yeah. Oh well. Yeah, so if you Google it around, I'm sure you'll find something for it. They got proofs of other random stuff, but not that one in particular.
okay.
Not that it matters too much. You won't be using it. There's no real reason to know it, other than just for fun. The main one you'll need to be able to do is calculating e of x squared, which, if you're basically following with what we were doing before, it's a transformation on the x. So e of x squared therefore means you're squaring all these x values before you do the multiplication. So 0 squared times 0.2, 1 squared times 0.15, and so on and so forth. You use that to calculate variance. So variance is a measure of spread, how far out the data set is spread. And you calculate it either using this fancy equation up here, or this is just effectively the expanded version of that. E of x squared minus E of x all squared. So we looked at how to calculate this one, we looked at how to calculate this one, so we're just doing the exact same methods and then chucking them in a subtraction.
Wait, you just cut out. Could you go over that again?
Yep. So variance there is going to be a measure of spread of the data set. And so the way you end up calculating that one is given by this equation here. I don't necessarily recommend you use that. You're better off using the expanded version of that in equation 2. We've looked at how to calculate e of x squared. We've looked at how to calculate e of x. What we've got to do is now square it and then do that little subtraction there. So there isn't anything necessarily new here. You've learned how to do both of those just now. You just put it into practice. And if you want to know why you probably shouldn't use this version of it, well, this is what the math looks like.
Yeah.
Versus if you do it this way, it's you calculate e of x like you've done before, e of x squared, which is still not particularly pleasant, but it's better than having additions and subtractions in these brackets as well. Just like how you can do e of x with a function inside, you can do variance with a function inside of it. This is highly unlikely to show up in an actual exam. In fact, it's never shown up in an exam. I'll say that much. But it'll show up in the textbook. You could just skip them, I guess, because it's not super relevant. But if you do want to get just some basic practice in there, just in case of like sacks, for instance, then basically just refer to. I mean, if it does show up, it's very likely we're going to use this simplification. If not, just use this one, which you may notice is very similar to the variance equation you're already used to, which is you're doing e of x squared minus e of x all squared. You're just replacing every x with whatever the transformation is. So if you have like ax plus b, for instance, you would now have e of ax plus b all squared in that spot. Kind of like how you deal with regular transformations.
Yeah.
And then there's just a whole bunch of shit here to show you how that looks like, but it's so unlikely there's really no point. Standard deviation is always the square root of variance, no matter what. So it doesn't matter what type of way you use to calculate variance for all the different probability types, you're always just going to square root that at the end to get your standard deviation. It's also a measure of spread. There's a bunch of reasons why we do it. It'll vary from application to application. I can't say for certain why we're doing it specifically in or what it's done in methods, or why it's done in methods specifically, but it's just basically another way of representing your data.
Yeah.
One of the things you might consider is the fact that it basically brings all the data closer together. Like if you have really, really big numbers and really, really small numbers, the square root impacts bigger numbers more than it does smaller numbers. And so it just sort of, I don't know, brings everything a bit closer. That's one thing to consider with why you would bother going with standard deviation over variance. But fundamentally, they're basically the same thing. Standard deviation is used a lot more though, especially with your confidence intervals, where you're doing you're centered at the mean, that's the mu symbol there, plus minus some number of standard deviations either side. So, if you got mean plus and mean minus a number, then the mean is going to be the center of that interval. The key ones you need to know are going to be the 68, 95, and 99% confidence intervals. You'll need to know those numbers and the relative spacing in terms of standard deviations, specifically for when we look at normal distribution. But as far as when you're calculating specifically a confidence interval, you're pretty much only ever using this one, the 95% confidence interval. So if we need to calculate it for discrete, which is pretty rare, and the only reason why it's quite rare for this is because you get kind of nonsense answers. Confidence intervals are usually best suited when you have a lot of different outcomes, like you're doing sample sizes of in the 400, 500 or so. Because what you'll find is if you do it on something as low as 4 possible outcomes, you calculate your mean, you calculate your standard deviation, and then you put it in the equation. I mean, the interval is bigger than the entire sample set. So we are 95% confident that our result is going to be between negative 0.23 and 3.23, which obviously is bigger than that entire thing. Maybe just for, if I pull up binomial statistics, we can see one that makes a decent amount more sense. Like if we calculate a confidence interval for this, for instance, it's going to come out to 304 to 336 because we're using a sample size of 400. And we can say, yep, the relative confidence we have for this number of successes is going to be between 304 and 336. All that to say, much more useful for higher n. I don't really see this a lot. And the reason this is in here in the discrete chapter is because it came up in someone's schoolwork once ever. And so might as well track it. That's pretty much it. Mean, variance, standard deviation. They're pretty much all calculated the exact same way. You're just doing some form of multiplying x's by probabilities and then either chucking that into a further equation or so on.
All right. Let me do some questions.
Yeah, we can do some questions. Get out a binomial. We want to be here. All right, 13D, question 1. Tickets in a game of chance can be purchased for $2. Each ticket has a 30% chance of winning $2, 10% chance of winning 20, or otherwise it's a loss. How much might you expect to win or lose if you play 100 times? Sort of let you just have a think about that before I give any input.
Is it going to be a table, a probability table?
Yep, creating a probability table would be a good idea.
Okay. Let me remember how these are made. x and probability of x equal x, I think.
Yep, yep. You'll have little x on the top, and then probability big X equals little x.
On the top, would you want like 2, 20, and then, or would it be like 1, 2, and 3?
1, 2, and 3, I wouldn't go with that. That would be a bit tough because it's
Oh yeah.
a fair bit removed from what you're actually tracking here, which is how much you're winning or losing. Um, the 2, 20, and 0 would be a bit closer to what you want. Yeah, you can go with that. Um, the other thing you might want to consider would be whether you're trying to do just pure winnings from the game, or whether you want to also factor in the initial cost as well. You can put in the cost afterwards, or you can put it in the actual table. Both would be, I think, reasonable.
Is it win $60?
If it wins $60, I'm pulling up the answers in the background. Forgot to grab them. Where are we? Yes, $60 is correct. That's good. Just out of curiosity, did you include the initial cost in the table,
Yeah, on
or
the table. I thought
yeah,
it'd be probably easier to do it that way.
yeah, it'd probably be a lot easier, I'd say, because um, what numbers go in the table are kind of whatever. It's whether you want to do the mean and then factor it in, which is a second step, or just do the mean and then multiply by 100.
Yeah.
Yeah, that's chill. Cool. Question two is just that again, basically, but you're not multiplying by 100 at the end. So, unless you want to practice on massive tables, you could probably move on from that.
Wait, why would we be multiplying by 100 at the end?
Oh, I was talking about this one.
Oh, okay.
Yeah, that was the 100 times. Um, yeah, it's just more things like that. Do you want to practice any more of those where you're trying to understand how to create the table first, or do you want to move on to like variants?
Um, yeah, I don't mind. We can. I'll do question 4 real quick.
Yep, easy.
I think there's gonna be a catch with this one. I think I can already see it
Okay, I
with
haven't read it
the.
yet, so let's see.
Is it 66 cents?
66 cents is a bit big, and it's positive as well, which should be a negative, or should be a loss. Okay. When you created your table, what did you? Well, maybe did you create a table?
Nah, I thought I could do without a table.
Yeah, I mean you don't really need it. It's only there for visualization fundamentally. So what was the idea?
If they win, it's $4 profit, and
Yes.
the chance of their number getting picked is 1 in 6.
Okay. Well, that all sounds good.
So you multiply it, and
What about when you lose?
I thought it was like just like one go, like one bet.
Yeah. I mean, even if it is one bet, you still.
All right. Oh, I didn't factor that in. I see.
Yeah. Okay.
So would it be like a loss of 34 cents?
You're probably are you just estimating the cents? Did you get like negative a sixth?
I got 66 cents at the start, and then I thought -$1.
Oh no, because it's $1 multiplied by the 5/6 chance of you getting that loss.
Right.
So basically, what you're ending up doing is, if you have a look at like how maybe you create the table for it, you got a $4 profit with a 1/6 chance. You got a -$1 for a loss with a 5/6 chance, and so you do your 4 by 1/6 plus the -1 times 5/6. Um,
Right.
so this is why the table can potentially help. It doesn't really change the math per se. You still are just doing 4 times that and -1 times that, but just having it in the table sort of makes it look like something you've done before, I suppose.
So around -17, -18 cents.
Yeah, yeah, something like that. But yeah, that's all. It's a very similar question to, in fact, it's basically the exact same thing, whether it's a ticketed game of chance or whether it's, I mean, spin is basically just a game of chance. Yeah, cool. Any more of those you want to practice?
No, it's okay. We can
That's
go
okay.
on if you.
Cool. So that's the E of X type stuff. They do have a few transformation style things in there, but you'll kind of also get a feel for that if you want to play with the variance. Um, Want to practice that variance?
Yeah, sure.
You need to get your p-value first, which is probably a good one to play with anyway a little bit.
P is 1/16. I should have said that
Yeah,
earlier.
yeah, p is 1/16.
I started doing thing
Yeah, that's
ELX.
fine. Yeah, variance is the main thing anyway. I had a feeling you get p. We've had a look at a couple of those before.
Is ELX 2?
The E of X is 2, yes.
Yeah, and I'm just about to do variance.
Yeah, which is kind of nice in these because you need E of X to do variance anyway.
Yeah.
Sort of leads into
23 on
itself.
2,
23 on 2.
11.5.
Not quite. Maybe you
Oh
added
wait,
them
it's
instead of
minus. It's
subtracting.
a
Yeah,
minus. I see.
yeah.
Should be 7 on 2.
7 on 2. That's it. Yeah. E of x squared minus e of x all squared. Yeah. Not much else to talk about. They're just long and a lot of calculations.
Yeah, the numbers are pretty okay with this one, all even.
Yeah. I mean, this one's chill. When you get decimals, it becomes a bit yuck. Um, I've seen some crazy. Yeah, look at that. Not fun.
Tech free as well, damn.
Yeah, I mean, you would think it's tech free since it doesn't say CAS, but I'm fairly certain this is tech active. I think they're just bad at saying whether it's CAS or not. Um, yeah, I don't know. I don't think there's going to be too many other differences around here. You're going to be basically creating your table, and then from there doing either E of X variance. You might see some slightly unique takes. Find probability of X being less than mean. Well, mean is just a number, which I guess is a good point. What happens when you get a decimal mean? How do you work with that? Let's say, for instance, I said the mean of this one was 2.5, just hypothetically, and I said find the probability of x being less than mean. What do you actually do? 2.5 doesn't exist on this table.
For a second, I thought I cut out again, but
Oh,
it's just that you're thinking.
oh no, no, I was asking you, what do you think you do there? Did you
Oh
did you
wait,
not
really?
catch what
Oh,
I
sorry.
asked?
Nah, and you probably did then
Yeah,
cut out.
okay. Yeah, then I probably cut out. So yeah, I was we had this question here, probability of x less than mean.
Yeah,
And my question there was, okay, let's say that we have, for this table specifically, a mean of 2.5. How do I find the probability x less than mean under those circumstances?
probability of X being less than the mean.
Yeah, so
Would you
effectively,
wanna would you wanna add actually no, that doesn't even make sense. I thought you were gonna add all those like outcomes together
mhm.
and then divide it by 4, but
Oh, okay. So if the statement probability x less than mean, effectively
oh
in this
wait,
case,
oh never mind, yeah.
yeah, got an idea?
So is it gonna be actually wait, but 2.5 is like
Yeah. So we'll
it's
say,
insane.
yeah, somewhere in between 2 and 3. Doesn't exist as an outcome, right? You can't find the probability of x being 2.5, not a thing. But the mean is 2.5 in this hypothetical.
Then like to find the part of like point 0.5 that's like lower than the mean, right? Would you want to add the probability of 2 and 3 and then divide by 2?
Not quite. So the statement here, if I were to basically write it out, would be find probability that x is less than 2.5, and you've got your 0, 1, 2, and 3. X less than 2.5 firstly just means the first thing you would ask yourself is what outcomes are less than 2.5? And so you just look at the 0, 1, and the 2, and you say, yes, those are the ones that I'm looking for. Then I just add up all those probabilities because now I know, hey, that's the valid outcomes in my end tool that's given to me. So you can indeed get decimal numbers in your probability stuff. You do get it with, wait, no, I was going to say you get it with sampling and estimation, but you don't really. Um, they can try to trick you in this way, where they'll give you decimals in there. You basically just either, if it's less than, you just go left of it to the nearest integer. If it's greater than, you just go right of it to the nearest integer.
Okay.
That's the way you handle that. The CAS does the same thing as well, by the way. If you do a CDF on the CAS in binomial and you give it decimals, it'll round inward. Oh, hang on, round inwards. Yeah, round inwards. So yeah, if you get something like that, that's how you handle that. Let's see, anything else? This is the whole variance, standard deviation, mean when you have stuff inside. You can practice it if you want, but that would take a while, and it just doesn't show up. Yeah, X variance, solve for K. 2 dice, X is the sum. This is going to be a massive table. But again, you create your table and then do your E of X and variance. Yeah, okay, nothing else in there. Cool, cool. Okay.
Wait, you know the question where it says if variance x is equal to 16? I think it's question 13. Yeah. So would variance 2x just be like 32 or
So for that, you would need to refer to this thing here, which is when you have ax plus b, it's the same thing as a squared variance. So
just 64?
yeah, because you bring in the 4 out here and then 4 by 16. Yeah, exactly. Um, so also then part B, if you've got x plus 2 there, effectively nothing happens. No constants change variance. This negative will get factored out and become squared, so again, nothing happens here. And this one, yeah, okay, so standard deviation is just square root variance. Actually, yeah, that is an interesting one then. What do you do there? Standard deviation, it would be the same as, oh, okay, I think I got an idea for this one. Before I say it though, I'm curious if you have an idea.
I want to say that you take the 3 out,
You want to take the 3 out is correct, yeah, at some point, but
and then I think you wait. If you square, if you square it for variance, then do you want to square root it for standard deviation?
yeah. So I think one of the first things I would do would be to say standard deviation 3x is equal to square root var 3x. And then from there, you treat it like variance, where you take the 3 out, square it, which we can kind of see where that's going, but yeah. X, and then using the square root laws, you're going to have 3 root var x. I don't know why I'm writing like shit on a slant. Let's fix that. Which of course just gets you back to 3 standard deviation x. I think that makes sense. That's the same as square root variance 3x. And then, yeah, taking that out.
Or it'd be like root 3 standard deviation x, but it's not.
Well, the square root laws is where you have, if you have square root AB, that's the same thing as root A, root B. That's what I'm doing here, which is distributing the root through both of these.
Yeah. So in our case, that'll just be 12.
3 times standard deviation of x, so you would root this down to 4 and then times, yeah. I think that's how it's going to work. Actually, yeah, let's check the answer on that one. 13D. Let's see if that worked out. Yeah, okay, it's exactly as I wrote it there. Yeah, so you got it. Good. 12. Sweet.
Cool.
Thinking hard. Okay, that's that one. And that is, yeah, that's all of discrete. Oh, sorry, no, it's not. Yeah, binomial. Right. Because I skipped ahead for the binomial statistics. Cool. Okay, binomial. Binomial is also discrete, although it's a particular kind of discrete. There's technically 3 criteria that makes it binomial. As far as what's actually going to matter in methods, you pretty much just want to see that there's 2 possible outcomes, either some success or some fail. That's pretty much it. To a secondary effect, you want to make sure that things are independent. So things like width replacement, for instance, you're resetting the experiment to the exact same state every single time. Um, that also matters a lot, but like in the vast majority of cases, if you can spot a easy success or fail, the question's going to have been written in the context of binomial. Um, the way we calculate those is with the Bernoulli sequence. You need to know n, the number of trials, x, the number of successes that you want, and p, the probability of a baseline success. So a simple example of that's going to be your coin toss stuff. If a coin is tossed 5 times in a row, that means n is 5. You're doing the experiment 5 times. What is the probability of tossing 4 heads? Well, tossing 4 heads is considered 4 successes in this case. And then lastly, it's kind of implied that a coin toss is going to be 50-50 heads or tails. So you use your p as 0.5. Again, crashed. Twice, unlucky. Oh no.
I might just start using my school laptop for these classes. I don't know why it happens on my home laptop so much.
Yeah, odd. Do you do any Zoom for anything else?
Not really.
Yeah, I was curious to see if maybe it showed up in your other Zoom
I did
sessions.
I did a 2 hour Zoom call a few weeks ago with someone.
Yeah.
But it was on my school laptop, I think, memory.
Okay.
And like he had like some like different sort of Zoom link. He had some Monash Zoom link, something like that.
Oh, sure. Yeah, okay, that's interesting. A Monash private link on Zoom. Yeah, I wonder if you can, I mean, I guess you can, obviously, if Monash have done it, make a unique Zoom link that has the, whatever hyperlink tracking stuff you want on it. But yeah, anyway. How far into that did I cut out?
I started here you like say like Bernoulli sequence and then
Okay, cool. So we use the Bernoulli sequence for calculating binomial probabilities. So you need to know n, the number of trials that you're repeating the experiment. You need to know x, the number of successes in the experiment. And you need to know p, the probability of a success. Success is going to be purely dependent on what particular variable you're tracking. In this case, we're tossing a coin 5 times, and we want to find the probability of tossing 4 heads. 4 heads is the desired outcome, and so we consider tossing a head a success. So this would make x equal 4, this would make n, the number of times we're doing it, equal to 5, and the p is assumed 50% since it's a coin toss, right? Heads or tails.
yeah. Can I just write that down real quick? The
Yeah.
Is that like a proper formula that you have to like remember? Or
This is on your formula sheet. So
okay.
I'll show you what it looks like on the formula sheet because it's kind of actually split up into 2 separate sections.
No, I know like there's like some probability formulas that are on the formula sheet, but I've heard like it's just better to like know them because I guess with practice you learn them anyways.
Yeah, I don't think I ever which ones? There was maybe the sampling and estimation stuff gets a bit weird, and you, or at least I referred to those in the exam if I needed it. But everything else is kind of you just sort of know them. Like the Bernoulli sequence, I never really had issue memorizing that. Um, it looks like
So
this.
N is the number of trials, right?
Yeah, and its number of trials,
P is
probability of a success,
yep, and is X
number of successes you're looking for.
right? Because when I was doing integration, like at first I used to like refer, but then as I like kept on practicing, I kind of just like
Hmm. Oh well, it's good that you.
got to remember them,
Yeah, even the integrals, nice.
the functions.
Yeah, some of the integrals I still looked up, like specifically this second tab integral. That one
Oh, that
was
one.
probably a lot, and probably the stuff with like the logs and 1/x's. Those are
Yeah.
pretty easy to mess up, but everything
No,
else is chill.
obviously I'm not like airtight. I'd probably forget some of them as well, but
Yeah,
for the most part, it's not too bad.
yeah. No, that's cool, cool. Because even with the sine and cos stuff, I have to like refer to the diff version in my head and then invert it. Um, Quotient rule used to get me quite a bit, but now I kind of just know it. And then, yeah, stuff like Newton's method and trapezoidal rule just didn't exist, or at least wasn't assessed. But yeah, as far as like what you'll see in probability, in your tech free anyway, you probably shouldn't have an issue memorizing this, but just know that it's in two spots. So you got the binomial coefficient, the NCR term up here, and then you've got the actual equation using it down here.
Right.
Yeah, and then here's just a very basic example of using it. If you're trying to calculate, just probability x equals something, you're just using a flat out Bernoulli sequence and then simplifying it down. On the CAS, this is the binomial PDF, which is under menu 55A, if I'm not mistaken. Don't crash on me! Really? Alright, that'll take some time to load. If you've got your CAS on you, it should be menu 55A.
Yeah.
And the syntax, if you're typing it out manually, is going to look like that. But you'll probably be using the setup wizard for it. It'll be fairly self-explanatory what each of the fields do.
My casual's in the same space as you.
All right, well, when it loads up, I'll revisit that, which is soon, actually. Either way, if you want to calculate over a range of probabilities, so anywhere from like upper bound and lower bound, tech-free, you're basically just adding up all the Bernoulli sequences in that interval, right? So it's the exact same way with discrete, where when we had x less than or equal to 1, it just meant adding up everything that was less than or equal to 1. So the same learning that we had before also applies, where if we had x less than or equal to 1.5, you just chuck that down to the nearest integer and then go from there.
Yeah.
Tech-free, you're doing 2 Bernoulli sequences here, which, double the effort, but not particularly fun. I have a little cheat sheet here, just make sure that you're keeping track of the inequality types. If you're non-inclusive, you do need to round to the next integer. Same as basically what I mentioned for decimals there. And for the CAS, that's going to be binomial CDF, which is right below the PDF. Is your CAS alive now?
Yeah. It's
Cool.
a lie.
So
Yeah, I found them. It's like they're both in menu 55, and then you just choose.
A and B. Technically, you can use a CDF for everything if you really wanted to. You just set the lower and upper bound to be the same number if you want to use it for a PDF application. But yeah, I mean, these are all the exact same things you've seen before. NP, and then lower and upper, or if you use the PDF, it's the X. The CAS always considers whatever you put in it to be inclusive in these spots, so just make sure you adjust for that. And if you give it a decimal, again, the CAS will just it knows how to work around that. Some tech-free ones might seem a bit excessive, like for instance, when you're trying to find probability of x being greater than or equal to 1, when you have 5 coin tosses, they're not quite expecting you to do 4 separate Bernoulli sequences back to back. You can leverage the use of complement probabilities by going backwards in the probability table. So just doing the thing that's not in the interval and 1 minus that thing saves you a hell of a lot of time.
Yeah.
These kinds of questions, I've got this written down now because, I don't know, at the time I thought this was probably the best way to go about it. Realistically, you can guess and check these. I'll go through it anyway, just so you can more or less understand the theory behind it, and then we can see how we go about it with a much more effective way. So the first thing you'll need to understand is how to get your head around the wording of the question. The probability of winning a game of chance is 0.25. What is the minimum number of games that must be played to ensure the probability of winning at least twice is more than 0.9? They're all kind of worded like this. This one sentence alone tells you 3 things that are necessary. So it's a very packed kind of statement. Minimum number of games. So what is the minimum number? So that tells you you're solving for n. Probability of winning at least twice, so x greater than or equal to 2. That probability needs to be more than 0.9, so targeting 0.9. Very dense question there. Fair enough where all those map to?
Yeah.
Okay, cool. Now, if you want to try and do this with as much algebra as possible, you're going to start with creating your actual probability statement. This one, you absolutely need the complement probabilities approach because n is unknown. If I say x greater than or equal to 2, that could mean 2, 3, 4, 5, 6. You don't really know where to stop. There's no n upper bound. But there's always a minimum of 0. They'll never, yeah, you can never get lower than 0 in most of these circumstances. We have seen, wait, no, actually, no. Flat out can't get lower than 0 for binomial because it's a number of successes rather than an outcome on a table. So it's a little bit different. So yeah, can't get lower than 0. So, just like we've seen before, if you're doing a tech-free, this means 2 separate Bernoulli sequences, which you'll simplify down, and then cas solve. If you're going to use this method for solving it, just make sure you put an equal sign there, otherwise the cas will just sort of not give you anything and just sort of spinning wheel of death, which is not what you want in the slightest. That'll give you 2 outcomes. The negative is obviously stupid because we're looking for a number of trials. And then all you've got to do is round the n value properly. This is always rounded up. I've never seen it round down, just simply based off of the fact that these equations are pretty much always the same thing, but with slightly different coefficients. But if you want to be double sure, you can just grab that probability statement that you have and just test at different values of n. Which one of those gives us a number greater than 0.9? Well, it's going to be the 15. Fair enough, the approach there?
Yeah.
Cool. Now, I don't recommend you actually do that, but it's nice to at least know how you can use complement probabilities and how you can create these equations. I guess in the very rare circumstance that they give you like a lot of marks for this and you have to show some working. But usually these are just multis. So what you do instead is you bring up your menu 55B to get a CDF going. You just guess a random number of n and you keep honing in on it. So let's say we started at n was 10. We were told p was 0.25. Yep. The lower bound is 2 here because it's greater than or equal to 2. And then the upper bound, of course, is just going to be whatever your n is. Then you're just going to hit OK and then be like, did I get a number greater than 0.9? I did not. So let's choose some other n. You can be fairly aggressive with it at the start and then just slowly taper down to getting closer and closer. Just use a bit of, I don't know, intuition to see how far you feel like you have to jump to the next number. If you feel like you're really close, do small changes. If you're far, do big changes. And then just make sure that you've found the actual minimum there.
Yeah.
And you can see how quick and basically brain dead that was. It doesn't take much effort.
I mean, I guess if it was a multi, we could just use the answers.
Yeah, even better, right? You can use the answers in there, and you don't have to guess. Yeah, even better, actually. Yeah, cool. That's those. And this is back when I put like 1 billion sample problems in the thing. My God. Yeah, I don't know how helpful this is for people, but it's there. This is when I had like this massive document of past exam questions. It was basically a bound reference.
I mean, I guess it's pretty useful for like independent study when I'm not doing it.
Yeah, I mean, I don't know. Do you want to have an 89-page document with everything in it?
Yeah, that's pretty long actually.
I'll drop it in here just if you want it, but I felt it was a bit excessive. But it does have everything. Like it's in fact, maybe even just the first little bit here where it's like an overview of how you approach probability stuff. Like First up, figure out what type of probability you have. Second step, now that you know what probability you have, these are the common variables that are talked about. N, P, and mean standard deviation for binomial. So maybe that front part will be helpful, just for like an overall guide. And yeah, anyway, that made it. Yeah, downloaded. Cool. All right, well, that's binomial calculating, binomial probabilities. Any of those sorts of things you want to practice? You're muted. Oh,
Sorry about that.
yeah.
The charm, I guess. It didn't totally take me out of the call.
Oh, cool. Okay. Yeah. Um. Yeah. So I was just asking, is there anything in there in particular you wanted to practice?
Probably you start with Bernoulli sequence.
Yeah. Yeah. Just getting some tech-free practice into Bernoulli sequence. Sure. Um. Yeah. Okay. Oh, you've already got it written down actually, so you can use that. Yeah. Let's see how well your notes go. So I don't know. Let's just say 14A. Nice and simple. Oh, sorry. 14A question 2. Maybe this isn't actually tech-free. I've just seen 4 decimal places there.
It's okay. I'll use it. I'll first input it in tech free on my page now. Put
Yeah.
into
Yeah.
the caps if need be.
Cool. What's crazy is I'm actually seeing ones that they have done relatively tech-free later on in the chapter. They've shown some actual workings for it, which has
Yeah.
some wild stuff. Hmm. I guess the main thing there is making use of common factors, taking out factorizing. That'll help a lot with these.
When I do my Bernoulli sequence, right? Do I want to equate it to 1/2?
Not equate it to a half. A half would be the p-value, the probability of success.
I
Because
see. Never mind.
what comes out of the equal sign is actually your answer. Find the probability.
Yeah. Okay, I think I can. Wait, actually, pretty straightforward to do a tech free for this one then.
Yeah, I mean, yeah, it's going to be varying degrees of half to the power of something. Um, but yeah, well, not a particularly nice number,
Yeah.
especially because I'm pretty sure there's a simplification of the fraction. So maybe keep them as their indexed forms as best you can before expanding all that out.
Holy. Okay. The fraction's pretty deadly. But
Yeah.
four decimal places, 1.8024.
Okay, well that's a bit off, unfortunately. 1.8024. What could be fixed there? Did you do the NCR term at the front?
Yes.
Okay. Was it 7 choose 4?
Oh yeah.
Yeah. Okay. Um. Cool. What else could have gone wrong? Did you input the Bernoulli sequence into the CAS or was it a PDF?
No, just like I did like whatever I could on my page, and then I the
Oh,
whatever like numbers I needed to yeah.
yeah. Okay, then it's probably just some simplification error. Because if we do exactly what it would have been, it would have been 7 choose 4 times half to the power of 4, because you want 4 successes. 1 minus that's obviously still just a half. And that is not what the answer says in the book, so what the hell?
I think I see where I went wrong there. Anyways. Um
Um, yeah, hang on. 2734. Oh, right, they rounded it in the book. Cool. Great.
wait, I think I might get it real quick.
Yeah.
Is it point yeah, same as you,
Mm.
0.2734.
Yeah, or at least as best we can, given the fraction. But yeah, yeah. Um, I didn't realize. Yeah, they. Oh, of course they would have rounded it. They said to 4 decimal places. Cool. Yeah. That's pretty much it. Being able to simplify the factorials and the indexes. Did you need to use much factorization to help with that? I
No,
imagine so.
not too much.
Not much.
It's maybe the selections equation when you're
Mm.
simplifying those down. It can
Oh
help to
yeah,
find its
sure.
expanded form.
Yeah, yeah, yeah. Makes sense. Yeah, I mean that's all Bernoulli sequence is. Just figuring out what the n and x is and the p, and a lot of the times I'll just flat out tell you.
Yeah.
Like if we score to any random whatever n
I mean,
is,
I guess it's just practice.
yeah, yeah, it's just gonna be practice. These sorts of things you probably don't need to practice too many of the basic questions on, because if you practice the slightly harder slash application style ones of them, you also practice the basics with that. Um, Only because these take a decent amount of calculation to get through. It's just a time saving thing, really.
Yeah.
Like you want to practice a few of these, saying exactly 2 means x equals 2, more than 3. No, well, they said exactly 3, so it's x equals 3. More than 3 would mean 4, 5, 6. Being able to practice those main things is going to be the more important bit than the actual arithmetic. Because I would hope you get basically unlimited practice of arithmetic literally everywhere in methods.
Yeah.
And this is actually a really dense chapter. Oh, that's a 22. Nice. All right. Well, that's that then. Um,
Yep.
yeah.
Cool.
Next lesson will probably be an exam thing, and then we'll crack back on the probability for the next couple.
No worries. Thank you.
Take care.